Okay, so the geometry of the molecules actually is depending on the bond angles as well as the repulsion of the between lone pair and also bond pair actually. Okay, as I told you yesterday, like water, right? It's not the linear. It is actually is a tetrahedral because the existence of the lone pair. Okay, it give a irregular shapes. Okay, because the lone pair is gonna be what is it, tend to repulse ataupun kita panggil push the bond pair. Okay, and the angles become uh, much closer each other. Okay. So there is a greater repulsion between lone pair and also between lone pair and also bone pair. Okay. So other sp3 covalents, if you look at here that this one CH4. Okay. This one also in tetrahedral shape. Okay. Methane molecules. Okay. Strong and difficult to break, like a methane has low melting point at negative 180 degrees C. Okay. Covalent bond between the molecules are strong and difficult, but the bond between molecules is weak and break easily. Covalent molecules have low melting point and boiling point. This one is more to like uh, how to say? Mm, kalau hydrocarbon is a single chain, right? Okay, so between the molecules is easily to break, compared to diamond. Diamond is like a 3D, like, okay. So this one is easy. Okay, so another example is hydrocarbon polymer. This one, germane, carbon tetrachloride. What else? Silicate ion. Okay, I want to share something. Actually, we can measure this geometry or predict geometry by using valence shell electron pair repulsion. Okay, so let me check. Okay, let me share this one. Okay, so if you look at here, okay, uh, this is the uh, how we predict the geometry lah. Okay, based on the bond angles. So if you look at here that there is a lone pair here, lone pair, right? There's a repulsion. It's gonna push this bond pair. Okay, that's why actually for water and also this one H2O and F2O. Okay, if by our observation we can guess it should be, how to say, just a linear, right? Okay, but due to the presence of the lone pair, okay, it's going to push uh, the bond pair. Okay, and the angle is become decrease from 180 degrees to 140 100 degrees, 104 180 degree to 104 degree. Similarly also ferrum F2O. Okay, because due to the repulsion of the electron pair. Okay. Okay, so I just show you. Okay, so this one. What's the difference between lone pair? Actually, it consists of two electrons in the same orbital from the same atom, which are not involved in bonding. So this is what we call it as a lone pair lah. This one. So if it's overlap, okay, in using the what is it? Between the valence, okay. Uh, During the covalent bonding, okay. So we call it as a bond pair because it's a form a pi bond or sigma bond. Sigma is more to single, pi is a double bond. Okay. Also non-bond pair, bonding pair. Okay. So that is about the what is the difference between lone pair and also bond pair. Okay. See this is the type of repulsion between lone pair and bond pair. Okay. Generally, if you look at here that bond pair the repulsion is lower than lone pair and bond pair, right? And lone pair is much greater lah, compared to bond pair, lone pair, and lone pair. Okay. Sorry, this one I just give some additional information to you because I teach quantum chemistry. Okay. This is what I told you about the irregular shape. Okay, bond angle decrease due to the presence of the lone pair. Okay, they push. Okay, and this one the angle is become decrease lah. Greater repulsion between lone pair and bond pair. Okay, and this one is just calculation. Okay, this one. This is the example of the water, right? Is the geometry is a tetrahedral. There's a many shape. Okay, by using a VSEPR is valential electron pair repulsion. This is how we predict lah, based on the calculation here. We can predict actually. Okay, so if you look at here, there's a many geometry. Arrangement of electron pair 180 linear, trigonoplanar. This one is the mostly we discuss today, right? Okay, trigonal pyramid and octahedral. Okay, so this is the example of the geometry and another one. Okay. So you can search from the Googles and I think you can get more information about the geometry and what molecule, different molecule have different geometry depending on the lone pair and also bond pair. Okay. Okay, let me share this one. Okay, so carbon containing molecules. Okay, carbon also can form multiple bonds. Okay, usually pi bond. Okay, double or triples and more reactive. For example, like aromatics, phenols, benzene. That is a double bond, but they have a resonant type. Okay, multiple carbon bond in carbon containing molecule refer to unsaturated bond. Okay, because it's difficult to cleave. Okay, that's why we call it unsaturated because it can be we call it as a resonant is the bond cannot cleave, it can move. Okay, can move. Okay, here this one, right? For example, this one can be here, so it can be like a resonant. It's possible. It's moving lah. Okay, especially for the benzene. Okay. Okay, so covalent bonding in benzene. This is I told you there's a in resonance structure is moving. Okay, if you still remember during your secondary school. Actually, this is the not the correct how to say. It's just a simplification. Actually, is a moving, right? One, this one, this one. That's why it's become here. And this one also. Okay. 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 So usually covalent bond in benzene is how to say uh, if look at here, this is the explanation. In benzene, covalent molecules have low melting and boiling points. Okay, covalent bond between atoms molecules are very strong and difficult to break, but the bond between molecules is weak and break easily. Okay, is solid brittles. Example of the aromatics like what is that? The combination of it's like a tar. Okay, tar from the we call it a solid product from the biomass. Okay, it can form the molecule structure from the aromatics. Okay, that is one of the example. Okay, so all these carbon network solid typically have a high strength, hardness. Okay, brittle. What else? The covalent solid number of neighbors around an atom depend on the bond order. Okay, bond order is how many bond can pair. Okay, with their neighbors. Okay, so all this actually you can is to is worthy lah. Okay. Okay. So that's all about the covalent bondings. Okay. Any question about the covalent bondings? Okay. So I think this is clear. Okay. So we move to the metallic bondings. Okay. So for the metallic bondings, as I told you, is more to the is not we call it as a bonding. It's more to the electron cloud. Okay. So the properties usually the materials is a strong, okay, difficult to break, like a stainless steel alloy, right? Is malleable, okay. Even if you heat it, is melt first, okay. If you what is it hit it by using the hammer, right? It's not gonna break like a ceramics, okay. It's gonna be ductile. It's a ductile properties lah, okay. Excellent conductor of the electricity, okay. So due to the what is it? Uh, due to the electrons, like a sea of electron, right? Okay. So it can be excellent conductors for the electricity. Okay. And then actually it's very strong, right? Okay. Since a very strong, each metals held together by the strong bond. Okay, because it's a metal or some is a non-metal, right? Mostly it's metal lah. Okay, so that's why it's become really really ductile. Okay, compared to covalent bond or ionic. Okay, so yeah, this is the the information about the metallic bonds. Okay, as I told you, it's very strong ductiles. This bond also allow atom to move because metals are ductile. No electrons transfer between atoms, no ions. It's more to the sea of electrons. Okay, metal have only 1 to 3 valence electron. Okay. So actually, the atoms in metal is closely packed in the crystal structure. Okay. So that one is compared to amorphous. Amorphous is a short range order, but for the crystalline structure is a long range order. Okay. The atoms arranged in 3D patterns. Okay. 3D patterns. Okay. Sebab tu kalau tengok yang metal ni dia punya form tu solid kan. Okay. It's so solid. Okay. Okay, so the formation of metallic bond, closely packed in crystal structure. All atoms contribute their valence electron to form a sea of electron. This one, sea of the electron, for cloud of electron, or sea of electron. Okay, electron charge cloud. Uh, this is delocalized. Uh, moving lah, benda tu delocalized. Okay, same like resonance lah, is delocalized or moving. Move freely among atoms. Okay. And do not belong to any specific atom. They are called free electron. This one we call it free electron. Okay. What else? No electrical neutrality restriction. Can flow electric. That's why you have to be careful with the stainless steel alloy or aluminum. Okay. No share localized electron pairs between atoms. Okay. Since valent electron are mutually shared by any electron, metallic bonds are non-directional. Okay, if we compare the bond energies or melting point between the elements of the metals, for example, group 1A and 2A, okay, generally group 2A have a high melting point, or we call it melting temperature lah, as compared with the group 1A. Group 1A is such as like lithium, sodium, potassium, that is group 1A, alkali metals. And alkaline earth metals, beryllium, magnesium, calcium, right? So and so on. They have a high melting temperature, melting point. Okay, and uh, have a very strong bond energies. Okay, so you need a high temperature to break this bond for the group 2A. Okay, because bond energy and the melting point is depending on the number of valence electron. Okay, and the percent of the metallic bond. Okay, if we compare, we can I can which one? The comparison. Okay, this one. So if you look at here that calcium, potassium and calcium, right? See the melting point. This is much greater as compared with the potassium, right? The bond energy, this one also kilojoule per mole, much greater, right? So 1s to s. So actually it's depending on the valence electron. This is 1s2. This one is 4s1. Okay. So fewer the number of valence electron, attraction force between positive on core and electron cloud decrease. Bond is more metallic, melting point decrease. This is the meaning of the fewer of number electrons lah, because this one is fewer than the potassium, fewer than the calcium, right? Okay. Similarly, also if we compare, what else? But where? This one for DS2 and also this one lah, kan? Calcium SC apa? Okay. This one is not group 2A. I think it's group transition metal, I think. This one is titanium. Titanium definitely is have a high melting point. Okay. So this is the comparison. Okay. It's depending on the valence electron. Increase the number of valence electrons, increase the percent of covalent bondings. Okay. Meaning that increase the bond energy and also melting point. Okay. So yeah, this is the comparison between 1A and 2A. Okay. Lithium, potassium, sodium, when we compare with the CS berylliums, right? This is 2A. So is the metals for 2A is have a greater melting point as compared to 1A. Okay. So in terms of the properties of the metals, the strength is more malleable, as I told you, high density because it's close packed in the crystal lattice. Crystal lattice is the position in a 3D form. Okay. Excellent conductor of the electricity. Okay. Excellent conductor of heat. Okay. Similarly, due to the close pack of the each atom. Okay. Memang sangat dekat lah. Okay. That's why it can conduct the heat. Okay. Yeah, this is the properties. Okay. So it's ductile, right? Ductility when you give an external force, it's just a deform rather than it's break like ceramics. Okay. It's not fragile. Okay. Later in the next chapter, we will more focus on the metal and ceramics. Especially I think is a metal. Okay. Okay, so after metallic bondings, we have also mixed bonding actually. Okay, mixed bondings. Actually, the bondings can be mixed between ionics and covalent and metallic and also covalent mixed bondings. Actually, if you want to know this bonding is mixed or not, we can calculate based on the ionic character. Okay. So if you look at here that chemical bond of ions or atom can involve more than one type of primary bonds. Okay, if you look at here that ionic covalent mixed bondings. Okay. Most of covalent molecules have some degree of ionic bonding. Okay, meaning that with the certain percentage with the certain electronegativity difference, we can uh, we can have a mixture of ionic and also covalent bondings. Okay, because generally yes, covalent bonding have ionics. It's almost close with the electronegativity difference is almost close with the ionics bondings, right? And if you look at here that metallic covalent mixed bondings commonly observed in transition metals. Okay, this one is for A. Say what else? Between group 1A to A to group 6A, 7A lah. That one is the transition. Yang tengah-tengah tu kan dalam periodic tables. Okay. So how can we know the characteristic of mixed bondings? Okay, by using the equation ionic character. Okay, 1 minus epsilon XA minus XB power of 2 divided by 4. Right. So XA and XB is electronegativity of atom A and B. So for example, if we have a silicon and germanium, okay, let's say that A is a silicon, Okay, and germanium is atom B. Okay, so if you calculate and you can get the percentage is around between metallic to covalent. Okay, so this is a mixed bondings, meaning that either is graphene, okay, liquid crystal, adult semiconductor, transition metals, or alloy. Okay, and if when you calculate between 50% to 100, okay, is more too closely to the ionic bonding lah. Okay, this one is covalent right, diamond. Okay, so ionic glasses, complex salt, ionic ceramic lah. Okay, so 100% is exactly on the ionics. Okay, so this is how you calculate the ionic character to see the either the bonding is a mixture or not. Okay. Okay. So this is the boundary range is okay. You can see in the previous slide. Sekejap, eh. Okay. So it's similar like the previous. Okay. Any question about the primary bonding? Easy, right? Okay. Before we move to the secondary bonding. Okay. Yeah, I think no questions. So let's we move to the secondary bonds. Okay. Okay. For the secondary bonds, we can divide it into fluctuating dipoles and permanent dipoles. For example, if fluctuating is like it's just like a touch, okay, between two molecules or two elements like a hydrogen gas and hydrogen gas. Okay, they have a secondary bonds. It's just a fluctuate. Okay, van der Waals we call it as a fluctuate dipoles. Or between um, group 8A, what is it? Inert gas, right? Okay, argon and argon. Okay, they can have a different charge because the charge is moving. Okay, they have a positive and negative. If argon 1 and argon 2, argon 1 is moving more to the right side, positive. Okay, and then the argon 2, the charge also move to the right. Okay, there's gonna be how to say this one if the balance this one is move the charge, right, more to the right side, and this one also move to the right side. Okay, and there's a negative. Okay. There's a fluctuate dipole bond here actually. Okay, between the noble, this is an inert gas between noble gas, for example like nitrogen, not nitrogen, neon, argon. Okay, okay, so van der Waals is another example of the fluctuating dipoles. Permanent dipoles like a hydrogen bondings. Okay, hydrogen bondings because it's very very strong. Okay, so because they have a different in the permanent, they have a what we call is different on the moment dipole. Okay, if you learn later, maybe I will show you the dipole moment. The dipole moment, yeah, the dipole moment. Let me check. Yeah. So it's about the dipole moment. Okay, because uh, some of molecule have a polar molecule, some is neutrals. Okay, so the one who have a different in dipole moments that can form a permanent dipoles like a hydrogen bondings. Okay, so let's see this one about the fluctuating dipole. Okay, so if you look at here that the two types of the secondary bonds between atoms or molecules involving electric dipoles. Okay, fluctuating dipoles and also permanent dipole, also known as the van der Waals bonds. Okay, so can interact each other by electrostatic force, and we call it Coulomb force. Okay, Coulombic force. Okay, containing dipoles are attracted to each other by this force. Okay, kat sini. Kalau tengok kat sini kan. Okay, whether to decide. Okay, this is two electronegative lah. They have a dipole moment. Okay, so because the charge is going to be different, right? Okay. Okay, let's see the fluctuating dipoles. Very weak attraction force between complete atoms, especially in noble gas. This is what I already told you just now, right? Okay. Arise because of asymmetrically distribution of the electron charge. Right. Because this one is symmetrical. Asymmetrical, this one, the charge is moving to this side. And this one is positive. Okay. So it's changed with the time. Okay. This is the one who can create the dipole moment. Okay. It's just a weak interacting non-directional bond. Okay. So if you look at here that liquefaction of noble gas at high pressure and solidification at low temperature. Okay, this is due to fluctuate of dipole bonds. Okay, if you look at here that they have different what is it? The different charge, right? Not different charge. It's moving. The charge is like moving to this side. Okay, this is nucleus. This one is a electron. Okay. So this one we can see that they have a fluctuating dipole. It's like it's a macam kita touch sikit lah kan. Macam tu lah. Okay. So also for the covalent molecules, symmetrically covalent bonded molecules having noble gas configuration like a hydrogen. Okay. Cl. So for example, this one between hydrogen, right? This one is hydrogen. H2, ini H2 lah. Possible also have a fluctuating dipole. Okay. Or Cl2. Okay. It's a gas lah. This is gas. Okay. Okay. So let's see. This is the example like argon. Right. Okay. So can have this is positive, negative, positive. So can form a van der Waals bond. This one is more to gas lah. Just like now is about the covalent molecules. It's possible to form the fluctuating dipole. Okay. Okay. So that's an example about the fluctuating dipoles. Okay. So let's see the permanent dipoles. What is the difference? Okay. So for the permanent dipoles, okay, from the polar covalent bonds, actually we can see this concept. Okay. The molecule that contains polar covalent bonds are called polar molecules. Okay. Polar covalent bonds, we refer to the unequal sharing of valence electron between bonded atom. It caused by the different electronegativity, right? So it can result on the polar bond, and which can give rise on the permanent dipole moment. Any heteroactive molecules, meaning that contoh dia lah. For example, like this one, if you still remember about the dipole moment. Okay. For example, CH3Cl. So CH3C H H H, and this one is Cl. Okay. So actually it's D plus. This one is D plus. Okay. And this one is D minus. This is more electronegative. So there's a dipole moment. All the arrow towards the C. And this one is towards Cl. So meaning that this is have a net dipole moment. Compared to, for example, C, right? Cl, 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 Cl. Okay. So for this example, if you look at here, this is more to negative. Okay. Okay. This is no dipole moment because all arrow towards Cl is become neutral. Okay, it's cancel each other. So this is no net dipole moment. This is what we call it as a permanent dipole moment. Okay, heteroatomic heteroatomic molecule. This one heteroatomic molecules. Okay, faham ya? So especially for the polar molecules. Okay. Okay. Uh, Actually, from the what is it? From the dipole moment, okay, or polar moment, we can know also the shape of the molecules, whether V shape, trigonal, or tetrahedrous. Okay. Okay. So this is the example. CH4. Right? This is another example. Example. This one is no net dipole moment because all the arrow, negative arrow, is all towards the carbon. This one. This one. 0 is cancelled. But this one is towards the Cl. This one, no dipole moment. This one is another example. If you still remember. Mu is equal 0d depth. Depth, I think is a measure in depth. Is it depth? If I still remember. Okay, it's column metric. If you look at here, the permanent electron dipole is created due to the permanent unequal electron charge distribution in the molecule. This one. Okay. They have a permanent dipole. Okay. Stable and does not fluctuate with times. Okay, different, not fluctuate, different with the fluctuate dipole moment, and fluctuate dipoles. Okay, and then what is it? Weak bonding force, permanent dipole bonding are created when molecules interact with each other. They have a electrostatic attraction. Okay, important in the bonding of polar covalent bond molecules such as water and various hydrocarbon. So for example, like a water, right? Water and water, H2O. They have different dipole moment, right? And also H2O. And they can create, what is it? Hydrogen bonding. Kena kira untuk formula ke? This one is just different of the, kita kena guna ni lah, different in electronegativity lah. Kalau Cl, electronegativity dia berapa? Cl ni. Kita boleh tahu kan? Cl 3.166. Yang ni C karbon berapa? C 2.55. 2.55. Hydrogen. Without the calculation also we can predict to which direction actually. Look at here that this one is electronegativity. This one 3.16 the electronegativity, and another one carbon 2.55. What else? Hydrogen 2.20. Right. This is more electronegativity. And okay, so meaning that is toward the Cl lah. Okay. Okay. Faham eh? So kita just boleh predict. No need to calculate also we can predict actually. Okay. The unit is in depth. Okay. 2.16. Okay. Kita kena kira guna formula ke untuk dapat pemahaman. Okay. So mu saya lupa lah dia punya equation. Sekejap saya check. I check the equation. But not necessary to calculate. Okay. Where's the equation? I did not include. Okay. For the dipole moment. Okay. But this is just a general. But based on the comparison, if you look at here that electronegativity, right? This one, okay. So we can now is they have a dipole moment toward the CL. Okay. Yeah, saya check dipole. What's the equation? Mu equal to QR. If I still remember. Yelah, betul-betul. Equal to QR. Okay. But this one, Q is the electronegativity. R is the, what is it? The radius. Okay, the radius lah. Okay. Dia mu lah. In that. DYV. Nanti you cari lah. Ni. But for this one, I don't think we will cover. Okay, this is the equation. Q is the magnitude. Okay. Opposite sign. Okay, maksudnya dia punya charge. And then distance R. Okay. 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 So let's see. This is a hydrogen bondings as I told you. Okay. The hydrogen bondings is permanent dipoles. Okay. For example, this one is a water, right? Okay. If you look at here that the interact electronegative atoms O and Fl Cl with the hydrogen, right? This one is O. This one is H. Okay. If polymer is such as like how to say? Polymer is like a cellulose. Okay. Cellulose is the made from the glucose monomer, right? Okay. Glucose monomer, if you still remember, if you know lah, cellulose, hydrogen bonds. Okay. Is a glucose paling senang macam ni lah. Okay. It's gonna have a right. Cellulose. If polymer lah. If polymer. Okay. So actually this is N. So and another one, if there's another one, it can what is it? Form hydrogen bonding also. Okay, with this one H, right? So this one O H lah. Okay, molecules. Between monomers also possible. Okay, to create the hydrogen bonding. If there is another this one, if okay, and this one have a OH. Okay, this one also can form hydrogen bonding with O here. Okay, so possible, and another molecule also possible. Okay, and it is very strong. That's why if for cellulose they have a amorphous is a consists of the amorphous and also crystalline structure actually. Okay, it's asymmetric arrangement of hydrogen atoms. Okay, okay. So that's an example of the molecules. This one is from the water. Okay, different charge, right? For negative and also positive similarly. Okay. Yeah, this is for the polymer. This one is for what is it? Between O and H. Yeah, O and H. Okay. Strong covalent bonding here and secondary bonds. Okay. And similarly, also this one can form. I think between this one also can form hydrogen bondings. Okay. Okay. So I think you understand. No need to explain in deep. Okay, so this is the explanation about the polymer that can form a hydrogen bondings. Okay, like amide, carbonyls, right? With the adjacent change. Okay, you can read this one. Look at it, the PVC and dipole bondings between Cl, Cl, CCl. Okay, so all this one you can read. Okay, the explanation. I just explain about the how to say the concept of the bondings. All this one I think you can read. Okay. Any questions? Okay. As a summary, I think for the bonding and the materials, I think actually you have to know about the covalent bonding, okay, metallic bonding and also ion bondings. That one is the primary. Another one is the secondary lah. So we call it as a tetrahedral structure. Okay, ionic, metallic, and also covalence, and then some secondary bonds. And secondary bonds we can divide it into fluctuating and also permanent. Okay. For example of the bonding for the metals like a metallic. Okay. A metallic is the metals. Okay. Ionic or covalence can be ceramic. Polymer can be covalent and secondary, and semiconductor can be covalent or covalent ionics. Okay. Okay. And then bond energy is different between ionic, covalent, metallic, okay, and also secondary bonds. Okay. Generally, for the ionics have a high melting temperature as compared with the, but actually can be mixed. Okay, the bonding can be mixed depending on the percentage or ionic characters lah. Okay, so as well as the valence electrons. Okay, so I hope that you can understand this topic for this chapter. So that's all the summary about the uh, uh, throughout of this chapter. So any questions? Okay, this is the difference. Okay, so you can read this one about the summary. So we are finished. Yes. It can affect the shape. Okay. For example, example right. Example like yeah. Okay. For example, like water, right? This is a more to V shape nitrogen. Actually tetragonals okay. And then nitrogen, right? It's not really the geometry. It's just a shape. Okay. Arrangement of the bonds lah. Okay. So for example, this one, right? NH3. And this have a trigonal pyramid. Okay. What else? This one like a Cl. 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 Okay, but this one they have no lone pair, right? Okay. So it can be tetrahedral. It can affect also. Okay. Okay, but this one also depending on the lone pair lah. Okay, this one also depending on there's a lone pair or not here. I don't think so. There is 5, right? So that's why the shape is like this one. So you're gonna pyramid. Okay.